All right, let's dive in. Today, we're pulling back the curtain on the absolutely wild technological arms race that powers modern finance. It's a world where fortunes aren't just won or lost in minutes or seconds, we're talking about microseconds. That's millions of a second. So, how on earth does it all work? And why is every single nanosecond worth fighting for? Let's get into it.
I mean, just think about that for a second. It sounds kind of crazy, right? A millisecond is a thousandth of a second. It's literally faster than you can blink. And yet, you have these firms spending fortunes, laying their own private fiber optic cables, even building microwave towers, all to shave off a few more nanoseconds. So, why? What is so incredibly valuable about that tiny sliver of time that justifies these massive, massive expenses?
Well, to really get it, you need to know that there are two totally different leagues when it comes to speed in this world. First, you've got low latency. This is the millisecond level stuff. It's fast for sure, but you can get there with high-end off-the-shelf hardware. But then you have ultra low latency, or ULL. This is a whole different universe. We're talking sub-millisecond, microseconds, and nanoseconds. And just look at that cost difference. Going from low to ultra low isn't a small step. It's an exponential leap in cost, in complexity, and in pure engineering brainpower.
And that brings us to the first really big idea here. This whole race for speed, it's not just some tech nerd's obsession. No, it's a cold, hard, strategic business decision. It's a race where every single nanosecond is put on a scale and weighed against potential profit. You see, different trading strategies have completely different needs for speed. A day trader, for example, might be totally happy in that low latency world of milliseconds. But for a high frequency trading firm, an HFT, being first to the market, even by a single microsecond, that's the whole ballgame. Their strategies, things like statistical arbitrage or market making, they're only profitable if you are the absolute fastest, period.
So here's the bottom line. Firms don't just blindly try to be as fast as possible. That's not how it works. They figure out exactly how fast they need to be for their specific strategy, and then they budget for it. That insane cost for an ultra-low latency system has to be justified by the profits that it can generate. If the math doesn't work, if it doesn't pay for itself, they just don't build it.
Okay, so now that we get the why, let's dig into the how. We're going to follow the journey of a single trade as it zips through one of these incredible high-speed systems. At its heart, every single trade follows this basic path. First, bam, market data comes flying in. Second, the firm's secret sauce, their strategy logic, instantly analyzes that data and decides to make a move. Third, and this is super important, a mandatory risk engine has to check the trade to make sure it's safe and compliant. And finally, if it gets the green light, the order is fired off to the exchange. All of this, the entire journey, has to happen in a tiny fraction of a second. Now, these systems aren't just one giant piece of code. Think of it more like building with super high-tech, specialized Lego blocks. You've got a component called a feed handler, and its only job in life is to grab market data and clean it up. Then you've got an order management system, or OMS, that's an expert at just sending the trade. Each piece is an absolute pro at its one specific job. And this brings us to a really critical piece of the modern puzzle, the transaction-based investment book of record, or IBOR. You know, in the old days, a firm might only know its exact financial position at the end of the day. But in high-speed trading, that's just not going to cut it. You need a live, real-time bank statement that tracks every single thing you own, every position, every dollar, instantly. Without this, real-time risk management is just impossible. Okay, so we've got the architecture down, but how do you make it that fast? I mean, mind-bogglingly fast. This is where the real engineering magic kicks in. Let's look at the secrets these engineers use to hunt down every last nanosecond. It really boils down to three main pillars of optimization. First, you get as physically close as you possibly can. Second, you tune your hardware and your operating system to within an inch of their lives. And third, you basically create a secret, high-speed shortcut for your data to travel. Co-location is the easiest one to wrap your head around. The speed of light is a hard physical limit. You can't break it. So, to make the signal travel faster, you have to shorten the distance. It's that simple. So firms will pay enormous fees to put their servers in the exact same data center as the stock exchange, sometimes just a few feet away, connected by the shortest, straightest piece of fiber optic cable possible. Now, kernel bypass, this is where things get really, really clever. Think of a normal operating system's network process like a bunch of security checkpoints at an airport. It's safe, sure, but it's also slow. Kernel Bypass gives the trading application a special backstage pass. It lets it skip all those lines, all those checkpoints, and talk directly to the network hardware. It's a huge source of speed, but man, you have to be an incredibly careful programmer to pull it off.
So, you've built one insanely fast trading engine. That's great, but how in the world do you make it handle millions of messages per second without grinding to a halt? The challenge of scaling up is just as intense as the race for pure speed.
Now, the answer here is going to sound completely backward. You'd think you just throw all the computer power you have at the problem, right? But for the most critical part of the trade, engineers do the exact opposite. They isolate the whole task on one single, dedicated CPU core. This gets rid of any tiny delays or unpredictability, what engineers call jitter, that happens when a computer tries to multitask. It's like giving your most important task its very own private, empty superhighway.
So if that's how you get speed, how do you get scale?
Well, you don't make the highway wider, you just build more highways. The system slices up the market, usually by stock symbol. So you'll have one engine on one core that does nothing but handle trades for Apple. Another one handles Google, a third one for Microsoft, and on and on. You run hundreds of these hyper-optimized, single-minded engines all at the same time, in parallel. And how you slice up that data really depends on the job at hand. If you just want to spread the trading load out evenly, you might use something called hash partitioning. But if you need to pull up all the trade data from last Tuesday between 10 and 10:05 a.m., range partitioning is way more efficient. It's all about picking the right tool for the job. We've covered speed, and we've covered scale, but there is one last piece of the puzzle, and it is absolutely non-negotiable: safety. In a world where trades happen automatically in microseconds, you have to have rock-solid safeguards to prevent disasters and to follow some very strict rules. And that is the job of the risk engine. Before any order can leave the firm, no exceptions, it must pass through this gateway. It's the system's circuit breaker. It is the firm's first line of defense, and it checks every single trade against all the rules. Position limits, credit, regulations, you name it.
Okay, but hold on a second. This brings up a huge problem, right? We've just spent all this time and money engineering a system to be as fast as humanly possible. And now we're going to force every single trade to stop at a mandatory checkpoint? Doesn't that just create a massive traffic jam and undo all of our hard work?
And the answer is, yeah, it absolutely would. Unless, that is, the gateway itself is also operating at a ridiculous speed. Get this. The entire time budget for a modern risk engine to grab a trade, run dozens of complex checks, and give it a thumbs up is often less than 100 microseconds. Engineering that is one of the most extreme challenges in this entire field. And pulling that off means using very specialized tools. You wouldn't use a cargo ship to try and win a speedboat race. For the super fast internal messages, the hot path, they use systems like Aeron. For slower, non-critical stuff like just logging everything for an audit trail, a system like Kafka is perfect. And for talking to the outside world, they use the old industry standard, FIX. Different tools for different jobs. And finally, the whole system has to be completely bulletproof. This all comes down to two key metrics: RTO, which is basically if it breaks, how fast can you recover, and RPO, which is how much data can you afford to lose. For these high-frequency systems, the answer to both of those questions is pretty much zero. You have to recover instantly, and you cannot lose a single transaction. And this brings us right back to our big question at the start. We've seen the incredible engineering, the strategic thinking, the safety nets that define this world. But as we keep pushing closer and closer to the actual physical limits of speed, from microseconds to nanoseconds, and maybe even beyond, you really have to wonder, in a world where success is measured in atoms of time and where failure is simply not an option, where does this technological arms race finally end? In the world of finance, there's this constant battle, this high-stakes balancing act going on every single second. On one side, you have this absolute need for perfect, meticulous control. And on the other, a relentless demand for lightning-fast speed. So let's dive into this fundamental tension because it really drives the entire industry. You can think of it like this. Every financial firm is basically fighting a war on two fronts. The control front is all about making sure every single trade is compliant, that it's accurate, and that it leaves a perfect paper trail for the regulators. Then you've got the speed front, which is all about getting the absolute best price by hitting the market with the lowest possible latency. You just can't win without mastering both. So, that brings us to the billion-dollar question, right? The one that everyone from Wall Street to Silicon Valley is trying to answer. How on earth can you be perfectly controlled and incredibly fast at the exact same time?
Well, to solve this puzzle, the industry developed two very specialized and, for a long time, totally separate types of systems. Let's meet the contenders.
First up, you've got the Order Management System, or OMS. The best way to think about it is as the air traffic controller for a portfolio. Its job isn't speed, its job is safety and order. The OMS is what portfolio managers and compliance officers use to create orders, check them against all the rules, and then track them from start to finish. It's the system of record, the single source of truth.
Now meet its counterpart, the Execution Management System, or EMS. And if the OMS is the control tower, the EMS is the fighter jet. It has one single mission: execute that trade at the best possible price with just blinding speed. This is the trader's cockpit, totally packed with real-time data, advanced algorithms, and a direct line right into the markets.
And this table really just lays it all out. Look at how these systems are designed for completely different masters. You have the portfolio manager, who's thinking about long-term strategy and compliance, versus the trader, who lives and dies by microsecond advantages. This isn't just a tech difference, it's a fundamental clash of cultures and priorities, all happening inside the same company. Okay, so you have these two separate, super specialized systems. The problem, of course, is that they have to talk to each other, and yeah, this is where things get really complicated. So this is the classic clunky workflow. An order is born in the super controlled world of the OMS. Then it has to be sent over, often manually, to the high-speed EMS. The trade gets executed, and then the results, the fills, have to be sent all the way back to the OMS to be checked and balanced. This whole round trip is often slow and just full of risky manual steps. So here's the crucial point. That handoff between the systems is a really fragile bridge. And when data gets mismatched, you get compliance gaps. When information is delayed, traders lose faith in the system and they start using their own manual workarounds. Suddenly, this huge investment in technology is undermined, all because the data just can't be trusted.
And the stakes here could not be higher. Regulators are watching this fragile bridge very, very closely. As this quote makes crystal clear, failing to perfectly link the original order to its final execution can lead to massive penalties. This isn't just an efficiency problem anymore. It is a huge compliance risk.
And guess what? There's a ticking clock. In the US, the SEC is rolling out the Consolidated Audit Trail, or CAT, which is this massive regulatory project to track every single order event across all markets. And they've set a hard deadline, January 31st, 2026, to solve this exact data linkage problem. The game of passing data back and forth is officially over. Integration is no longer a choice, it's a mandate. So with that fire lit under everyone, how is the industry responding? Well, this brings us to the next generation of platforms designed specifically to solve this exact dilemma. The solution is actually pretty elegant when you think about it. Just combine them. The Order Execution Management System, or OEMS, merges the control of the OMS with the speed of the EMS into one single unified platform. No more clunky handoffs, no more fragile bridges. It's one system, one source of truth. But even with an integrated system, the race for speed is never, ever over. In a normal computer system, a command from a trading application has to travel through all these different layers of the operating system, the kernel, before it even reaches the hardware. And every single one of those steps adds precious microseconds of delay. And this is the brilliant solution, kernel bypass. It's like building an express lane that lets the trading application talk directly to the hardware, completely bypassing all that operating system traffic. This is the secret sauce for achieving the kind of ultra-low latency that high-performance trading absolutely demands.
Now, layer on top of all that incredible speed the power of artificial intelligence. Instead of just using static roles, AI-powered systems can actually learn from every single trade. They can find the smartest path to execute an order, they can predict market moves, and they can even automate routine tasks, which frees up the humans to focus on the big picture.
But, and this is probably the single most important rule of AI in finance, an algorithm is only as good as the data you train it on. If your data is fragmented or untrustworthy, remember that whole integration dilemma? Your AI is going to be useless. This is why solid data governance is the absolute bedrock of any of these next-gen platforms.
So with all this speed, all this integration, and all this AI, what does it mean for the actual humans on the trading floor? This chart tells the whole story perfectly, doesn't it? In the past, a trader's day was all about manual execution, clicking buttons, typing in orders. In the future, that manual work just shrinks dramatically, and their time is spent supervising the automated systems and algorithms that are doing all the heavy lifting. So here's the key takeaway. Technology isn't replacing the trader, it's promoting them. The human role is evolving from someone who processes things manually into a strategic supervisor. It means they have to understand how the algorithms work, they have to know when to step in when market conditions get weird, and they're constantly looking for ways to make the automated strategies even better. Their job becomes less about doing and more about thinking.
Which leaves us with a final and pretty fascinating question to chew on. As these integrated AI-driven systems get closer and closer to executing the perfect trade every single time, what becomes the new source of competitive advantage? What is that unique edge that only a human can provide?
In the world of tech today, systems are so complex that things break in ways we could never see coming. So, we're going to explore this massive shift in thinking. A move from just knowing that something is broken to being able to ask exactly why it broke. This is the journey from monitoring to true observationality.
So, let's kick things off with the core of the problem, this idea of unknown unknowns. Now, these aren't just the bugs you haven't gotten around to fixing yet. No, these are the problems you don't even know you could have, the kinds of failures you literally could not anticipate.
And here's the kicker. In today's world of distributed software, these are the things that are actually causing outages. Failures don't follow a neat little script anymore. They bubble up from these tiny, completely unexpected interactions between dozens of different services. And that right there is a huge problem for our old ways of doing things.
And all of this really leads us to what we can call the complexity crisis. The way we build software has completely changed, and frankly, the tools we used to rely on just can't keep up.
Think about it. Modern apps are this whirlwind of dynamic microservices. Services spinning up and down, all spread across the cloud, talking to each other through events. In this kind of chaotic world, a failure isn't just one thing breaking. It's the result of countless tiny, unpredictable interactions. Trying to find those unknown unknowns with a handful of preset alerts, it's like trying to catch rain in a thimble. It's just not going to work.
Okay, so faced with this crisis, what's the industry doing? Well, it's not just about building better tools. It's about a complete and total shift in philosophy, moving away from being reactive with monitoring to being proactive with observability.
And this analogy just nails it. Monitoring is that check engine light flashing on your dashboard. Something's wrong, but you have no idea what. Observability? That's the mechanic plugging their computer into the diagnostic port, getting all the raw data, and being able to ask any question to find the exact sensor that's failing. See the difference?
So let's really break this down. Monitoring is great for known unknowns. You set an alert for when CPU usage gets too high. But observability is designed for the unknown unknowns, those weird problems you could never predict. The whole question changes from a simple, is it broken, to a much, much more powerful question. Why is it behaving this way?
And this is so important to get right. Observability isn't a tool you can just go out and buy. It's a characteristic of your system. It's a measure of how well you can understand what's happening on the inside just by looking at the data it puts out. You don't buy it, you have to build it in from the start.
All right, that all sounds great in theory, right? But how do you actually do this in practice? How do you balance shipping cool new features with, not letting the whole thing fall over? The answer lies in a framework called Site Reliability Engineering, or SRE.
The whole SRE framework starts by getting really, really specific. First, you define your service level indicators, your SLIs. These are the concrete things you measure, like latency or uptime. Then, you set your service level objectives, or SLOs.
And these are the exact targets you promise your users you're going to hit. So, for instance, a team might set an SLO of 99.9% uptime for their service. This isn't just some vague promise to try our best. It's a hard, quantifiable target that clearly defines what good enough actually looks like. And here's where the magic happens. If your target is 99.9% reliability, that means you are explicitly allowing for 0.1% unreliability. And that 0.1%, that's your error budget. It's the precise, calculated amount of failure you have permission to spend.
Think of the error budget like money. It becomes this organizational currency. Do you want to launch a risky new feature that might cause some instability? Okay, that will spend some of your budget. But if you spend it all and run out, all new feature development freezes. The whole team has to pivot and focus only on reliability until you're back on track. It's a brilliant, data-driven way to manage that classic tug-of-war between moving fast and staying stable.
Okay, so we have our targets, we have our budget. But how do we know if we're on track? Where does all this data come from? Well, this is where the pillars of observability come into play. These are the different kinds of data signals, or telemetry, you need to be collecting to get the full picture. Let's walk through these data streams. First, you have metrics, which tell you what is happening, the raw numbers like CPU usage. Then you have logs, which tell you when. They give you a chronological story of events. Traces show you where a request went on its complete journey through all your services. To go even deeper, profiling reveals the why by pinpointing inefficient code. And finally, you have packets, the ultimate truth of what actually happened on the network. And you know what's really powerful here isn't just having these different data types. It's the questions that each one allows you to ask. Metrics tell you, flat out, are we meeting our SLOs? Logs help you answer, what was the exact sequence of events that led to this failure? And profiling can tell you precisely, why is this service so slow, right down to the specific line of code. Each pillar is a different lens for asking smarter questions. So you're sold on collecting all this data. Now comes the really big question. What tools are you actually going to use? And generally, the choice boils down to two main paths. You either build your own stack with open source, or you buy a commercial platform. On one hand, you've got open source. The huge plus here is total flexibility. And of course, no license fees. But the downside is pretty big. You have to stitch it all together yourself, which takes a ton of engineering time and can have a surprisingly high hidden cost. On the other side, commercial platforms give you this polished, all-in-one solution with cool features right out of the box. But you'll definitely pay for that convenience and licensing fees, and you'll have less control to customize it. And here's a quick look at how some of the big names in this space fit into that picture. You've got Prometheus, which is a beast for real-time metrics, but you need other tools to complete the picture. You've got Datadog, which is trying to be that all-in-one, seamless platform. And then you have Splunk, whose real superpower has always been its incredible log management. The takeaway here is that there's no single best tool. It's all about what makes the most sense for your team's needs, budget, and expertise.
So, what's next? Where does this all lead? Well, once you've built a solid foundation of collecting high-quality data, the future is all about making that data smarter. And that's where AIOps comes in, using AI for IT operations.
This stuff is a potential game changer. AIOps promises to take observability to a whole new level. Instead of you waiting for an alert to fire, machine learning models can spot weird patterns proactively and find issues before your customers ever notice. It can automatically connect the dots between all 5 pillars to find the root cause in seconds, not hours. And in some cases, it can even trigger automated fixes without a human ever having to touch a keyboard.
But, and this is a huge but, you have to remember, AIOps is not magic. It is only as good as the data you feed it. If your foundational telemetry, your metrics, logs, and traces, is incomplete or just plain messy, your fancy AI platform will be completely useless. It's the classic garbage in, garbage out. Getting the fundamentals right is everything.
And that really brings us full circle, back to a final question for you. As you look at the systems you build and manage every day, ask yourself this. Are you just monitoring for the problems you already know how to look for? Or have you actually built a system that is truly observable, one that gives you the power to ask any question you can think of and find the answers to problems you haven't even imagined yet? The difference is everything.
All right, let's dive right in. Today, we're going inside the engine room of the digital world to really understand how your favorite apps can suddenly change and get better, almost in the blink of an eye.
I mean, have you ever had this happen? You open an app one morning and boom,
There's a slick new feature that just wasn't there the night before. How in the world do they do that? How do they roll out these massive changes so quickly, so reliably without, everything just breaking? It's a great question, and honestly, the answer has completely changed the game for how software gets made.
Well, the secret is a concept we call the software factory. And I want you to get that old image of some dusty, manual workshop out of your head, the kind where a new release might take 6 months, maybe a year. Nope, we are talking about a sleek, modern, high-speed assembly line for code that literally never sleeps. And today, you and I are getting a full tour. Okay, so first things first, we need to understand the blueprint. This whole factory runs on 3 core principles. 3 levels of automation that all build on each other. So let's break them down. It all kicks off with something called continuous integration, or CI for short. Just think of this as the factory's loading dock. Every single time a developer finishes a new piece of code, even a small one, they merge it into a central hub. The second it arrives, an automated process kicks off to build it and run some initial quality checks. Now, this was a huge shift. Instead of waiting months to mash everything together and just hope for the best, the idea is to check tiny changes, but do it constantly. It's all about finding and fixing problems right away.
Next up, continuous delivery. So, after our code passes that first check at the loading dock, it moves on to the main assembly line. Here, it goes through a whole gauntlet of really intense automated tests. And if it passes everything, what you have at the end is a fully finished product. It is always ready to go, it's packaged, it's polished, and it's just sitting there in the warehouse, waiting for a real person to walk over and hit that big green Ship It button.
And then we have the final, most advanced stage, continuous deployment. This is the factory on full autopilot. If a piece of code makes it through every single one of those automated tests, we're talking quality, security, performance, the whole shebang. It doesn't wait for anyone. It doesn't ask for permission. It's automatically shipped right out the door to you, the user, instantly. The only thing that can stop it is a failed test. That's it.
So let's just put it all side by side. You've got CI for frequent testing, continuous delivery to get the product ready to ship, and continuous deployment to ship it automatically. The real dividing line, the big question, is that human date for production. See it there? With continuous delivery, a person makes the final call. With continuous deployment, the machines are in charge. And that one little difference says a ton about how much an organization really trusts its automated factory. Okay, so we've got the theory down. Now, let's get our hands dirty. We're going to follow one single piece of code on its entire journey through this factory, all the way from a developer's keyboard to your screen. You can really break this whole journey down into 4 simple stages. First up is source. That's just where a developer writes the code. Then it goes to build, where that raw code gets compiled into something a computer can actually run. We call that an artifact. Next, and this is crucial, is the test stage. This is our quality control department. And finally, deploy. That's when the finished, tested product gets sent out into the world.
But let's double-click on that test stage for a second, because this is where the magic really happens. This isn't just one simple check. Oh no, it is a gauntlet of automated tests. You've got unit tests, checking the tiniest little nuts and bolts, integration tests, making sure all those parts work together. You've got end-to-end tests that literally pretend to be a real user clicking through the app. And then layered on top of all that, you have tests for performance and security. And here's the kicker. If a piece of code fails any single one of these tests, the entire assembly line grinds to a halt. Red light, stop, nothing gets through that isn't top-notch.
Okay, our code made it. It passed every test. It's ready to go. But now, how do you actually get it to your customers? You can't just flip a switch and send a brand new thing to millions of people all at once. What if there's a bug? That would be a disaster. Well, this is where the factory gets really clever, using some very smart shipping strategies.
2 of the most popular are blue/green and canary. With blue/green, imagine you have 2 identical environments running side by side. All your users are on the blue one. When the new version is ready, you deploy it to the green one. Then you just flip a single switch and all the traffic instantly moves over. If something goes wrong, flip the switch right back. It's super fast, but yeah, it's expensive because you're running double the infrastructure. Then there's the canary deployment. Think of the old canary in a coal mine idea. You release the new version to a tiny group of users first, maybe just 1%. If everything looks good, you slowly, gradually roll it out to more and more people. It's fantastic for limiting the blast radius if a bug does sneak through.
But what if you wanted even more control? That's where feature flags come in, and they are brilliant.
Imagine a simple on-off switch that a developer builds right into the code. This lets you do something amazing. You can ship the new code to everyone's devices, but keep the feature switched off. So it's deployed but not released. Then, when you're ready, you can flip that switch on for just your internal team, or for 10% of users, or for everyone, all without doing another deployment. It's like the ultimate safety net.
Okay, so we've been deep in the weeds of the assembly line. Let's zoom out a bit. Let's look at the master blueprint for the entire factory, how it's designed, how it's secured, and how it's all managed.
A huge evolution here is the shift from a push to a pull model. In the old days, a central server would push updates out, but that meant that server needed the keys to the kingdom, all the sensitive credentials to access the live environment. That's a huge security risk. The modern approach, called GitOps, flips this completely. Now an agent inside the production environment simply pulls in the updates it's supposed to have. The central server never holds the sensitive keys, which makes the whole system way more secure. And speaking of security, it's not just a final inspection at the end of the line anymore. Today, it's about weaving security into every single step. This philosophy is called DevSecOps. You have automated scanners looking at the raw source code for bugs, other tools checking all the third-party components you're using, and even tools that attack the running application in a test environment to find weaknesses. Security becomes part of the process, not just an afterthought.
So we've seen all this incredible technology. But why? Why go to all the trouble of building this sophisticated digital factory? Well, the answer comes down to real, measurable business value. We measure the factory's performance with what are called the DORA metrics, and they basically measure two things: speed and stability. How fast can you get new ideas out the door? That's your velocity. And how reliable is your product? That's your stability. How often releases fail, and how quickly you can recover when they do, because things will go wrong. A great factory isn't just fast, it's fast and stable.
And the impact is just undeniable. Just look at this data. By automating their factory, one company cut the time it took to deploy software by a staggering 87%. Think about that. That's a shift from waiting weeks to deploying in just a few days or even a few hours. And that time saving, it translates directly into innovation. That same company saved over 150 senior engineering hours every single month. That's like getting a whole extra person's worth of time every month freed up to build new features instead of being wasted on manual checklists. But here's what might be the most important takeaway of all. The best factory in the world is useless without the right culture. This entire system is designed to break down the old walls between the people who develop, test, and run the software. It forces collaboration and shared ownership. Without that human element, the technology simply won't deliver on its promise. Culture is the secret sauce.
And that really brings us to our final thought. When you have a factory this efficient, this fast, and this reliable, the question is no longer, can we build it, but what should we build next? It completely changes the scope. All right, let's dive right in. Today, we're tackling a huge topic in software engineering: performance tuning. Now, this is so much more than just fixing a few bugs. It's really about building systems that are fast, efficient, and ready to scale right from the get-go. So, where do we even begin?
Well, it usually starts with this question, the one that haunts every single developer and drives every user crazy. You know the feeling. That dreaded lag, the spinning wheel of death, the timeout error. It's a universal pain point for sure. But the answer isn't to just start guessing and making random changes. No, it's about a systematic, data-driven hunt for the real culprit.
And to kick off that hunt, we need to focus. So let's start with just one number, a really powerful number that's going to guide our entire strategy today. 80%. Just let that sink in for a second. What on earth could this mean? Well, it turns out, that's right, this is the classic Pareto principle, the 80-20 rule, but for software. What it's telling us is that the vast, overwhelming majority of your application's slowness is probably crammed into a tiny fraction of your code. So this is great news. It means our job isn't to optimize everything. Our job is to be detectives, to find that critical 20% and pour all our energy right there.
So to do that, here's our game plan. We're going to start with the absolute bedrock framework for tuning, called the MOOV cycle. Then we'll start peeling back the layers of what I like to call the performance onion, starting with the code itself, then digging into the database, and finally zooming all the way out to look at the whole system architecture.
Okay, first up, the absolute foundation. Before you even think about changing a single line of code, you have to embrace the MAOV tuning cycle. This is the disciplined process that separates the pros from the people who are just chaotically guessing.
The mantra here is super simple. Data leads and optimization follows. And here's that cycle in all its glory. It's a simple loop. First, you measure, gathering actual real-world data on how your system is doing. Then, you analyze that data to find the real bottleneck, that 20% of the code we were just talking about. Only then do you move on to optimization, where you make one specific targeted change. And finally, and this is so crucial, you validate by measuring again. Did it actually get better? If so, awesome. If not, you go right back to the beginning. This process stops you from committing the cardinal sin of performance work, premature optimization.
So, what are we even measuring? Well, it really boils down to these three core metrics. Latency is all about speed. How long does one thing take? Throughput is about capacity. How many things can we get done in a second? And IOPS, that's a measure of how fast your disks are. But here's the key takeaway. These things are all connected. For example, if you improve your storage IOPS, that can lower your latency, which in turn could boost your overall throughput. You really have to look at all three to get the full picture.
All right, with our framework in place, let's peel back that first layer of the onion, the code itself. This is where performance begins and ends. If this foundation is shaky, the whole house is going to be slow, and it doesn't matter how much expensive hardware you throw at the problem.
Man, this quote says it all, doesn't it? You simply cannot buy your way out of a bad algorithm. Now, that fancy term, asymptotic growth, it just means how an algorithm's performance changes as the amount of data it has to chew on gets bigger and bigger. A fundamentally inefficient process will always be inefficient. It'll just burn through more expensive servers while it fails. This is exactly why choosing the right algorithm is probably the highest impact optimization you can ever make.
And how do we talk about this stuff? We use something called Big O notation. Now, don't let the name intimidate you, seriously. All it is a simple language to describe how an algorithm is going to behave when you throw more data at it. It's not about how fast it runs on your machine today, it's about predicting how it will hold up under the crushing weight of real-world traffic.
Let's just look at a super simple comparison here. An O of n algorithm, or linear time, is predictable. You double the input, you roughly double the time it takes. Makes sense. But an O of n squared, or quadratic time algorithm, well, that's a performance time bomb. You double the input, and you don't double the time, you quadruple it. It explodes. This slide shows perfectly how a seemingly tiny choice in your code can cause a complete and total performance meltdown when you scale up.
Okay, next up, layer 2, and this is a big one. It's one of the most common sources of bottlenecks in just about any application out there, the database. Your app spends a huge chunk of its life just waiting for data, so getting this part right is absolutely non-negotiable. So how do we tune a database? We have to start by looking at its secret recipe, the query execution plan. See, when you ask the database for something, it doesn't just randomly grab the data. It comes up with a whole plan for the most efficient way to get what you asked for. Understanding this plan, and I mean really understanding it, is the key to unlocking database performance. You have to know what the database is actually doing under the hood.
And a lot of the time, we make the database's job way harder than it needs to be with these common anti-patterns. Using select star forces the database to fetch every single column, wasting network bandwidth and disk I/O. Starting a like search with a wildcard makes your expensive indexes totally useless, forcing the database to read the entire table. These are such small mistakes, but they have huge performance costs.
The fix, thankfully, is usually pretty straightforward. Instead of select star, just ask for the exact columns you actually need. Write your filters, your where clauses, so they can take advantage of your indexes. And hey, if you know you don't have duplicates or you just don't care, use union all to avoid a pointless and really expensive sort. These simple little changes can literally transform a query from taking minutes down to milliseconds.
Okay, it's time to zoom out. Let's get to our final layer, the architecture. In today's world of microservices and cloud computing, performance isn't just about one machine anymore. It's about how dozens, sometimes hundreds, of different services all talk to each other and work together.
One of the most critical architectural choices is how your services communicate. In a synchronous or blocking pattern, Service A calls Service B and then just waits. It does nothing until B responds. So if Service B is slow, or even worse, if it's down, Service A is just stuck. This creates a really fragile, tightly coupled system. The modern alternative is asynchronous communication. Service A sends a message and then just moves on with its life. This decouples the services, making the entire system way more resilient and much, much easier to scale.
This slide visualizes that death by 1,000 cuts problem perfectly. Every single network hop between services adds a little bit of latency. 10 milliseconds here, 30 milliseconds there, it all adds up. Individually, none of them seem like a big deal, but from the end user's perspective, the total latency becomes a significant, really noticeable delay.
So let's put it all together. This hierarchy is just a fantastic mental model. You always start at the bottom. The OS and hardware decide how to schedule tasks and manage I/O. You build on top of that with the absolute fundamentals, efficient code and smart algorithms. From there, you make sure you can get your data quickly with database tuning. And finally, you wrap the whole thing in a solid architecture that can actually scale. Each layer builds on the one below it. You can't skip steps.
And that really brings us to our final and, I think, most critical question. Performance isn't something you just bolt on at the end. It's a feature you have to build in from the very start. So the question to take back to your team is this. Are you guys constantly reacting to performance fires, or are you actually engineering for speed from day one? Because that choice right there is the difference between building a system that's just functional.
All right, today we are plugging directly into the matrix of the global financial system. We're going to talk about the incredibly fast, high-stakes world of algorithmic trading. In this explainer, we'll unpack how regulators are even attempting to police the invisible, lightning-fast forces that pretty much run our markets now. So let's start with a big one. Can a few lines of computer code actually crash the entire global economy? I know, it sounds like something straight out of a movie, but this is the very real question that regulators are grappling with right now. And the answer? Well, it's a little scary. It's yes. Because it's happened before. That's exactly how long the now infamous flash crash lasted. In just over half an hour, a whole cascade of automated trades just sent the market into a terrifying nosedive, and then a wild recovery. It was a massive wake-up call that the machines were moving way too fast for any human to keep up. And this is the scale of the chaos. $1 trillion. That's how much market value was just, poof, erased, even if only for a little while. This one event proved that the risks here weren't just theoretical anymore. They were very, very real. Okay, so to really get how we ended up here, we need to pop the hood and look at the code itself. Let's break down the key technologies that are driving this whole high-speed revolution. So, at its heart, you have algorithmic trading, or AT, and all this really is using software to make trading decisions. Now, the really crucial part here, and this is based on the official EU definition, is that the algorithm is making the key calls. We're talking when to trade, at what price, and how much to trade, all with almost no human looking over its shoulder. It's not just clicking the button for you, it's deciding to click the button in the first place. And then you have high-frequency trading, or HFT. Now, HFT is basically algorithmic trading on steroids. It's all about one thing, pure, unadulterated speed. You've got firms spending millions on specialized gear, even physically placing their servers in the same building as the stock exchange's servers. That's what colocation is, all just to shave a few microseconds off their trade times. With HFT, there's literally zero human intervention. It's all machine. So you might be asking, why do regulators care so much? Well, it really boils down to these three things. They have to protect the market's basic integrity from being manipulated. They have to prevent one firm's rogue algorithm from starting a domino effect, a systemic collapse like the flash crash. And, at the end of the day, they have to protect regular investors from a game that can feel completely rigged. So, facing these massive risks, the world's two biggest financial superpowers have gone down surprisingly different roads. It really is a tale of two completely different philosophies when it comes to regulation. And this is where you can really see the split. On one hand, the EU and the UK have what you could call a fortress approach. They demand that firms build these really strong controls and run tons of tests before an algorithm ever goes live. It's all about prevention. The US, on the other hand, takes more of a detective approach. They focus on massive surveillance, recording every single trade so they can go back in time, CSI style, and find the bad guys after the crime's been committed. And you can see how those philosophies play out in the actual rules. In Europe, under a regulation called MiFID II, firms absolutely must have pre-trade controls, things like a mandatory kill switch that can shut down a rogue algorithm instantly. In the US, the big thing is the Consolidated Audit Trail, or CAT. Just think of it as a gigantic database that tracks every single order down to the millisecond, so they always have the evidence they need to prosecute.
So what kind of crimes are these fortress builders and market detectives actually trying to stop? Let's take a look at how these slick algorithms can be used to break the law. Okay, the number one crime in the algorithmic trading playbook is something called spoofing. To put it simply, it's lying to the market. An algorithm places these huge orders that it has absolutely no intention of ever completing, just to trick everyone else into thinking there's a huge wave of buying or selling interest.
So here's how the heist works. Let's say you want to sell some stock. First, you place your small, real sell order. Then your algorithm just floods the market with enormous, totally fake buy orders. Now, other traders see this wall of fake demand and think, whoa, the price must be about to shoot up. So they start buying, which actually pushes the price up. Your genuine sell order gets filled at that new, artificially higher price. And then, bam, your algorithm instantly cancels all those fake buy orders before they ever go through. It's a digital sleight of hand.
And make no mistake, the consequences for getting caught are very, very real. This is the fine that JP Morgan had to pay back in 2020 for years of its traders systematically spoofing the market. Yeah, that's nearly $1 billion.
So, and this is important, this isn't just some regulatory fine. Under US law, spoofing is a felony. Now you're probably thinking, how on earth do you prove intent when a computer program did it? Well, prosecutors don't need a confession. They just point to the algorithm's behavior, the systematic, repetitive, non-random patterns of placing and then instantly canceling huge orders. No legitimate trader would ever do that, so the pattern itself becomes the proof of intent.
But what happens when the code starts to learn, when it starts to think for itself? This brings us to the next and frankly, much more complicated frontier: artificial intelligence. This right here, this is the question that's giving regulators nightmares. You see, if a normal, predictable algorithm goes haywire, you can blame the programmer or the firm that used it. But what about a self-learning AI, one that adapts and literally rewrites its own logic based on what it sees in the market? If that thing causes a disaster, who's actually responsible? The tough reality is that the blame could be spread all over the place. Was it the developer who wrote the original code, maybe with a fatal flaw? Was it the investment firm that deployed it without having the right safety checks in place? Or what if it was the company that provided the training data, which accidentally taught the AI all the wrong lessons? It is a legal and ethical minefield. And this quote from the UK's top financial regulator really nails it. They're finding that often the root cause isn't just a piece of bad code. It's bad governance. It's sloppy documentation, nobody being in charge, and compliance teams who don't really have the technical skills to challenge the quants and programmers. The human systems built around the AI are proving to be just as important as the AI itself. And this all leads us to what you might call the central crisis in AI regulation today. It's this fundamental tug-of-war between the drive for innovation and the desperate need for control. Look, on one side, you have the trading firms. Their algorithms are their crown jewels, their secret sauce. They guard that proprietary code, the black box, with everything they've got. But on the other side, you've got the regulators, and they're demanding something called explainable AI. They need to be able to look inside that black box to understand why it made a certain trade, to check for hidden biases, and crucially, to figure out who to blame when it all goes wrong. So let's just quickly recap the main takeaways here. First, no doubt about it, these automated systems create huge new risks for the entire financial system. Second, the world's regulators are split on how to deal with it. You've got Europe building a fortress of prevention versus America doing detective work. Third, AI is throwing a massive wrench into everything, making it incredibly difficult to figure out who's accountable. And that leads to the final point. Good, old-fashioned human governance is not obsolete. In fact, it's more important than it has ever been. And we'll leave you with this final lingering thought. We are walking into an era where AI can learn, adapt, and even start to write its own new code. So as these digital ghosts in the machine get smarter and more autonomous, the biggest question of all is, who or what